Hello students, so in this lecture we are going to discuss about the Raman analysis of carbon based materials, and we'll also consider the nanocarbon materials like graphene, and see what can be derived from the Raman analysis. Now, Raman analysis is considered to be one of the most significant analysis to find for the structural characterization of carbon-based materials. Now, it is based upon the very famous three-stage Ferrari-Robertson model, where uh, the G peak and the IT by IG ratio obtained from Raman spectra has been associated with the different types of growth, liquidation and growth, and also based upon the different hybridization that has taken place with respect to those growth. Like if here this G stands for graphite, we assume that from graphite the crystallite size, if it reduces and forms a nanocrystalline graphite, and then it further reduces to form amorphous carbon, and then again there is a change in structure to form tetrahedral amorphous carbon. Now in graphite, 100% graphite, the hybridization is sp2 hybridization, but as we move from graphite to nanocrystalline uh, and further to amorphous crystalline, the sp3 hybridization and even sometimes sp hybridization takes place in the overall structure, and as the percentage of sp3 hybridization increases from nano amorphous carbon, the structure changes to tetrahedral amorphous carbon, that is towards the diamond structure. Now in a phase diagram, this can be represented by this fashion, where we have considered sp3 in one of the corners, sp2 in one of the corners, and hydrogen in one of the corners. Now initially, when the concentration is mainly sp2, it is graphitic, but as in the three-stage model, when the percentage of sp3 hybridization, the sp3 carbon increases, it moves to amorphous carbon, and then it further moves to tetrahedral amorphous carbon, and this is 100% diamond. In the same way, hydrogen can get incorporated into the material. So if in this place, where you can see that although there is carbon, there is diamond, but it has some hydrogen incorporation that has taken place, so it forms tetrahedral amorphous carbon CH. And whereas in lower cases, like in this case where the sp3 hybridization, sp3 carbon is less, it forms amorphous carbon, because here the tetrahedral sp3 carbon percentage is less, whereas in this case it is more. This region corresponds to your polymers, hydrocarbon polymers, and this region where mainly the percentage of carbon has reduced and mainly there is hydrogen, so we consider that there is no full formation here. Now the whole Raman spectra, carbon-based Raman spectra, can be represented by Mulliken symbols. They are symbols arising from the different phononic modes, Raman active and inactive phononic modes. So this is how it can be represented. Each of the terms like A2U, B2G, E1U and E2G, they have got significance. Like the first one, we'll start with this one, 2G. This is the mode which is considered to be a Raman active mode, and these modes are found at the following wave numbers. So this is actually the G band or the G peak, and this is however not observed in many cases. Mainly this is the one that is observed, so they are arising due to E2G modes. Like if you take any carbon based material, so you will find D and G band. D is called the disordered band and G is called the graphitic band, and G is as explained previously, it is mainly due to the sp2 carbon. So the more is the sp2 carbon, that is graphitic carbon, the more will be the higher will be the intensity of this G band. And the D band, it mainly represents disorder, or if there is some sort of clustering taking place, then this D band will increase in intensity. Also, if there are some polymeric chains, then this G band will shift either in this side or that side, and also this G band, due to clustering, it shifts away from the usual position of say 1580 centimeters. So the shift. Now, what are these G bands? This G band, that is the graphitic band, is actually due to the stretching modes of carbon. So we consider one single unit cell of carbon, hexagonal carbon. Then the stretching, that is, if these bonds they go inside and they contract and they expand. This is the stretching mode. This is the reason why we get a G band. Similarly, the D band, the disorder, is due to the breathing mode, when the bonds go out and in. So this actually leads to formation of the breathing mode, or D band. Now, the intensity has been usually gets plotted with respect to the wave number. It's 2 pi by lambda, or sometimes 1 by lambda, whatever will be the case. Now to analyze the formation of these bands, curve fitting is done. So we mainly fit the curves, which in this case there are two plots, two peaks obtained, prominent peaks. So we mainly fit it with a combination of a Gaussian and Lorentzian mixture, and after fitting, the parameters that are obtained are the full width half maxima, or the bandwidth of the plots, and the intensity. Now, the intensity, again, there are two types of intensities. One, which is the one that is the arbitrary unit intensity, and the second intensity is the integral intensity. You take the area under the plot. This is the integral intensity area. Usually it's better to take area under the plot, simply because of the fact that a peak may show an increased intensity, but it may also reduce in width. So if our main objective is to find how much of carbon concentration or a certain type of carbon concentration is there, it's better to take the integral intensity, because it will give you the true picture. Now, this is called a deconvolution. This fitting of the D and G peaks is called deconvolution. This is also done in the case of XRD. Now, why this deconvolution is necessary? Like the schematic that has been shown here, it is the D and G bands are quite prominent, but it may so happen, especially when the material is in the nanometer range, or the crystalline size is very less, that these peaks are not so prominent. Like, let's say you get a peak uh, like this. So in this case, if someone asks you to find out the ID by AG ratio, because that is required for finding out what type of growth has taken place, first of all, you need to do some background correction. You need to remove this amount of data, so that we get, if we remove this amount of data, the plot that we obtain is like this. It's called background correction. Now we need to fit it with multiple fits. This is how the fitting will be done. So the idea is that the area should match. I mean, these are the two. In fact, there will be two different. So not like this way. There will be say two plots obtained, two fits, one for the G and one for the D, and the fits will be done in such a way that the some of these plots will match exactly with the original plot. This is what the fit is. For more complicated systems, like we may get a peak in the form like this, more than 2 weeks, like we get peak in this form, right? So here it again it will be fitted. So this is the background direction. Fitted, we get 3 peaks. One small peak, and again this peak. Okay, so this peak might reflect something else. So this is the D, and this is the G. This might be sometimes there is a T peak, there is tetrahedral peak earlier to G peak. So this is how the deconvolution is done. Now coming back to what we were discussing, after the deconvolution has been performed, next the Mulliken symbols, like okay, so the G band, as you can see, which occurs around 15-18 centimeters inwards, is due to this E2G phonons, and they are at the Brillouin zone of the center. This will be explained later what is the Brillouin zone. Brillouin zone, from crystallography, you might know that there is something called the Wigner seed cell. That means we have the basic unit cell. Suppose you have a crystallographic pattern like this, and you take the crystal planes, they are again divided in such a way that in the energy versus K diagram, in the E versus K diagram, you obtain plots in this fashion. So there will be some regions where the electrons are allowed, and there will be some regions where electrons are not allowed. So this is minus K to plus K. So this is the first relay zone. This is minus 2K. This is minus 2K. So this is the second relay zone. So basically they are based upon the diffraction that the electrons, or sometimes the X-rays may take place, considering that material is in crystallographic pattern. So similarly, this E2G bond is the phonons, that is lattice vibrations at the Brillouin zone. They give rise to this G, or the stretching modes. D again is as told in the previous slide, related to clustering, and it is also due to disorder or impurities and like defects, and yeah, there is internally double resonance process is the reason of obtaining D, and they also represent interruptions in the pi carbon delocalizations. Now, let me explain this a little bit. Say the graphite. If you look at the structure of a graphite, the graphite has sigma bonds. These are the sigma bonds, and these are the uh, pi bonds. Now, in the graphite, uh, they can be in the graphene, since we are talking about few layers of graphene, the pi electrons here is delocalized. So they are less bound to the carbon. So this delocalization, it results into the graphene or the carbon nanotube to be having a semiconducting or conducting nature. Okay, and this is required. Uh, this is mostly this will occur when this sp2 hybridization is there. However, if sp3 hybridization starts to take place in the whole system, then these delocalization electrons are hindered. So that actually gives rise to this peak. So the interactions of the pi electrons decolorization as CH, that is sp3, forms. Now, again, this E2G that we have said to be the Raman active mode uh, can is found at 47 centimeter inverse and 1580 centimeter inverse. And if you take same crystals of graphite, you can see that how the bonds are linked, how the stretching actually takes place in graphite. So this stretching, these sort of stretchings, they will correspond to E2G, therefore a peak around 47 centimeter inverse. And if the stretching takes place in this fashion, it will the peaks will arise at 1581 centimeter inverse, and they are called highly ordered pyrolytic graphite, these zinc crystal graphites. And another thing about a compound being Raman active, uh, for it to be any compound to be Raman active, the necessary condition is the rate of change of polarization with respect to molecular motion. This should not be equal to 0 at the equilibrium condition. So let me explain what this actually means. It means that say if we have a diatomic molecule, say AB, and so there is delocalization of electron between them, between the A and the B molecule. So let us represent this delocalization as this fashion. Now, when this diatomic molecule, which is very simple explanation, when this is subjected to an external electric field, then there is chance of polarization. That means the positive and the negative charges may show some orientation, and which will lead to some electric dipole moment. So we can say that electric dipole moment arised is equal to proportional to electric field. Higher is the electric field strength, higher will be the polarization, and so we can explain it as mu is equal to alpha into E, and alpha is called the polarization, polarizability, polarizability constant. Now, this electric field, this is basically is from light. That is, light is electromagnetic field, so electric component of the light, it causes this sort of activity. Now, in this AB molecule, this molecule can undergo different type of vibrations. It can stretch like this, or it can bend in this fashion or this fashion. Now, instead of say AB, if the molecule is ABC, so if you compare AB and ABC, the stretching may not be as symmetric in ACB as in AB. This is mainly simply because that due to the fact that this ABC molecule can vibrate or stretch or bend asymmetrically. So suppose initially the AC molecule, the stretching is less, whereas the C and the B molecule, the stretching is more. So the average stretching is asymmetrical. Or also in this fashion, there may be different ways by which the molecule may show alterations. Now, what effect this alterations have on the polarization? Polarization that is observed by simply plotting change in polarizability with respect to or the rate of change of polarizability with respect to movement of the molecule or disruptions of the molecule. Now, for a molecule to be Raman active, this value should not be equal to 0 at the equilibrium condition. That means if ACB is stretching in this manner, the next stretch it can cause is ACB. Now, there is a huge difference between A and C now. These two should not be symmetric to each other. Only then you can have a Raman active. That is why for this d alpha by d eta by eta sigma, only those plots which have a positive and negative value like this may show a change in value at the origin. That is the slope at the origin. Only these values will be called Raman active. This is the reason why your carbon oxide CO2, if you compare two molecules CO2 and H2O, CO2 is Raman active. However, H2O is not Raman active, because in every stretching and bending modes of H2O, you will get a symmetric pattern. That means a positive and negative movement is complementary to each other. So this is equal to 0 in case of H2O. Like in molecular spectroscopy, the rotations should lead to a molecular change. Similarly, in this case, the polarizability change should not be 0 at equilibrium condition. Now, this polarizability again can be used to draw something called polarization ellipsoid. Polarization ellipsoid. That is, we brought a three-dimensional structure, where the distance from the center to one of the edges is equal to 1 by alpha. It is inversely proportional to the polarization constant or polarizability. Then if the structure of the shape form is an ellipsoid or a spheroid, which can be an oblate, a prostrate spheroid, like in the shape of a rugby ball, under this fashion, then it means that the polarization change is not symmetric, it's not isotropic in nature, and that may indicate that the material is Raman active. However, if we obtain this region to be spherical in nature, so it automatically indicates that it is not Raman active. Now, these things will be discussed in more details in the spectroscopic classes, spectroscopic lecture videos, which will be uploaded in due course. Now, coming to our lectures on Raman aspect of carbon. Now, coming back to the Mulliken symbols, uh, so this has been due to this Raman active modes. Now we know what this Raman active mode means, E2G formation. Now apart from that, we have three different symbols. Just try to understand what are them. Now these are then IR active, that is vibrations are causing change in polarizability and with a non-zero value at the center, or the heat or phononic movement. So they are represented by these two symbols, A12 and EU-E12. So only here E12 is being used, and A12, right? This one A2U. So these are for IR active. And the last one, this is an optically inactive symbol, and the IR active ones, that is the A and the B's, they are not the air active. It's one of the A's, and the optically inactive ones, they are out of plane displacements, whereas the E is the symmetric modes, and they represent in plane atomic displacements. Now, the Ferrari-Robertson model, the FR model, and which was followed by another model called the TK model, these two models could explain the variation of crystallite size based upon this intensity ID by Ig ratio. According to the TK model, this ratio ID by Ig, it is inversely proportional to the crystallite size. That means if there is an increase in the intensity, the electrical intensity of T, it will indicate, automatically it will indicate that the crystallite size are going down, that is LA are going down. However, again in the same way, if the Ig values they grow up, that is the graphitic intensity grow up, then it will be represented by an increase in crystallite size. But the Ferrari-Robertson model actually predicted quite the opposite. They say that if the crystallite size increase, they will indicate that the ID values A are also increasing and the G values are decreasing. Now these two relations are correct. The reason is that they apply to different stages of the Raman of the carbon growth. This is explained here. Here you can see So if the crystallite size is less than 20 Armstrong, that means in the nascent stage, then the ID by Ig ratio will be proportional to L square. So in this case, and the increase in crystallite size will indicate that there will be increase in this G band, and this in the T band, the disorder will be higher. However, after this threshold has been crossed, they follow the TK model, that is being inversely proportional to LA. So in this case, an increase in D will indicate that the crystallite size have gone down. Now, so based upon this model was created as we showed in the first slide. So here you can see that the crystallite size are going down in this case, and it has further gone down in this case, and it has gone up or down. This ID by Ig ratio, as you can see in this first, it is increased with increasing the slide size. That means it has followed this, the 1 by LA ratio. So ID by Ig in this case is proportional to LA square, showed an increase. Again, after this diamond graphite stage has been reached, it shows a decrease. That means it is now following the TK model. Okay, and it till a certain concentration of sp3 carbon. However, this G peak position, which indicates clustering and also the sp2 carbon, it has again, in the case of an amorphous carbon or uncrystalline carbon, it has shown a decrease, and when the carbon is attaining the tetrahedral amorphous carbon shape, again the G intensity, it has gone up. Now, coming to nano carbons, there is a nanocarbon called if we take the graphene, if we take the Raman spectra of graphene, very interesting thing that will be obtained is there will be almost no deep peak provided a pure graphene has been formed. So a pure graphene sheet, Raman spectra of a pure graphene sheet will not show any deep peak, any disorder. Instead, it will show another peak at around 2700 centimeter hertz, far away from this deep peak, and this peak is called the 2D peak. It is basically an overtone. In the similar way, there is another compound called graphene. That is, if we allow hydrogen to react with graphene, it forms graphene. Similarly, as alkene forms alkane, in a similar way, the graphene will form graphene, and it is a very good hydrogen storage material from the very fact that the hydrogen gets bonded with the carbon, and we can take it out whenever required. Now, the Raman spectra of graphene, on the other hand, will show that there is G peak formation due to the sp2 carbon, it is quite obvious, but there is a disorder. This D, this is mainly due to the hydrogen or the CH bond that is formed, and there is also some more overtones of this D. This is called D dash, which is formed just alongside the G band, and there is also formation of overtones with respect to 2D, that is D plus D dash. However, if we annihilate that, if we remove the stress and make the film more more pure, then these overtones, they actually disappear. This D dash and this D plus D dash, they disappear, and we get a DG and a 2D peak. This 2D peak is quite sharp if a graphene formation is taking place, whereas in the case you can see that it has gone broader, the slide size have gone down. Okay, so again in graphene there are no D peaks, only G peaks because it is less impure, and in fact there is formation of 2D peaks which are present even if there is the absence of defects. Now these 2D peaks is due to the uh, sum of two phonons with opposite spin, that is k and minus k dash. This will be taken up in next due course classes in due course, and explain what this where are these two photon system comes and how do they and why do they add up having opposite spins to create 2D. And also this D dash band, that is due to the internal double resonance, intervalley double resonance that arises. That is, we are talking about this small D dash band, which is also due to intervalley double resonance. So these are mainly the impurity states after the growth. Right. So this was all for Raman spectra of carbon nanomaterials, and as with demand we will create more detailed video of each and every aspect of what has been discussed here. Let us do a summary. So we of this course of this class, according to this summary, we have studied this that in the Raman spectra of any carbon based material we will get a D and a G peak. The peaks may be very less, intensity will be very less, or they may not appear based upon the intensity, based upon the type of growth pattern. Like in a graphene, we don't get these D1, we get only G and overtones, whereas in the case of graphene, where there is introduction of hydrogen, uh, the D peaks are obtained due to impurity, and apart from that D dash peak are also obtained, and D plus D dash are also obtained. So these are basically impurity peaks, so we require some sort of annealing to diminish these peaks and to obtain the D, G and 2D peak. Of course there is a G peak. So this again can be explained with the help of the Faraday-Robertson three-stage model, which is based upon thus ID by IG ratio and G peak position. This ID by IG ratio are the integral intensity ratios, which help to analyze the structural aspect of the material. And there are two regimes. So again this ID by IG ratio, they follow two rules. So at lower crystallite size they will follow LS square. The crystallite size is directly proportional to LS square for size less than 20 angstrom. However, for higher crystallite size they follow the TK rule. They follow the FR rule, that is 1 by alpha. There are the two rules, or two regimes. Okay, that's it for this class.